Scientists that wanted to probe microscopic nature of matter in different kinds of materials, synthetic or natural materials, using X-rays, ultraviolet or infrared. So the synchrotron was a powerful instrument for studying several aspects of matter. In fact, it's the most versatile way of understanding the microscopic nature of materials. I've been always using the Wolfram language as my language of expressing ideas and inspiring the teams that work with me. I'm probably the heaviest user of the Wolfram language in the lab. Language is the road or the path through which ideas flow, right? For me, it was always an easy language that I could quickly program. I mean, you learn the program, you have several languages that we all dominate, but the major difference is all is in your hand, and it's very graphical for analytical things, and you can mix analytical aspects of the language with numerical aspects and with graphical aspects.
We are here with Harry Westfhal for this nice interview. Harry is currently the director of the Brazilian Synchrotron Light Laboratory at the Brazilian Center for Research in Energy and Materials. Thank you very much, Harry, for agreeing for this interview. We're going to talk a little bit about your work employing Wolfram language, your work at the LNLS and the Synchrotron Laboratory. But first of all, I would like to highlight that you are one of the recipients of the Wolfram Innovation Award last year in 2025. So that's really nice. And before we start talking about specificalities, can you tell us a little bit about the Brazilian Synchrotron Light Laboratory?
Yes. Also, first of all, thank you very much for inviting me for this interview. It's a great honor to be here. It was a great honor to receive the Wolfram Award. And I'm a big fan of Wolfram, Steve, and the company itself. From the early days of the company, I've been a user of Mathematica for several decades. And so the Brazilian Synchrotron Light Laboratory is one of the laboratories of the Brazilian Center for Research in Energy and Materials. The name is CNPM. Is a non-profit private organization that's overseen by the Ministry of Science and Technology and Innovations. Is a center where we have several laboratories and also an undergrad school in sciences. And it's all started with the Brazilian light source. It was the first Brazilian light source back in the 80s. This was a big national project to construct with Brazilian technology a synchrotron light source. And this was very successful and created a community of synchrotron users. So basically, scientists that wanted to probe microscopic nature of matter, different kinds of materials, synthetic or natural materials, using X-rays, ultraviolet or infrared. So the synchrotron was a powerful instrument for studying several aspects of matter. In fact, it's the most versatile way of understanding the microscopic nature of materials. So the Brazilian Synchrotron Light Laboratory started in the 80s, constructing this lab with Brazilian technology. And that evolved for a much larger center with a larger scope than just synchrotron radiation back in 2010. And this evolved now what is a big center with a very vibrant environment for science in biology and materials and devices and nanomaterials and development of pharmaceuticals and development of enzymes for the green chemistry. And of course, we have now a new light source that the Brazilian Synchrotron Light Laboratory is responsible for managing. It's called Sirius, that replaced the old source. It's one of the only fourth generation light sources in the world. And I think along this conversation, I'm going to be more clear what is. But it's the, let's say, the last generation of synchrotron light sources. And today, the Brazilian Light Laboratory is responsible for providing experiments for our international community, is open for anyone in the world with good ideas to use synchrotron light to understanding how materials work at the microscopic level and how their properties emerge from this microscopic organization.
This is really nice. And talking about your role at the LNLS, what kinds of questions or decisions you are usually responsible for?
So I'm a little bit of history. I joined the laboratory back in 2001. And the laboratory LNLS started construction of UVX, the older light source, in 1987. 1997, this was opened. This old light source was opened for users. I joined the lab in 2001, and my role at that point was to provide theoretical background for the experiments that were being pursued in the lab. And so I was progressively seduced by the experiments. And back in 2007, I was already becoming experimentalist and taking care of some experiments close to the beamlines. And then this led me to designing beamlines, these instruments that use the synchrotron radiation. And in 2010, I became deputy scientific director and then scientific director in 2013. And in 2020, I took the role of director of LNLS, which I'm currently in this position. In 2013, also, I assumed the responsibility of the design and construction of the experimental stations, the beamlines of Sirius. So my role from that point on was to organize the teams, to create actually the scientific and engineering teams that would design, construct, and operate these beamlines for the future of a light source that didn't exist at that point. And so I had to not only work closely with the community on the science that we would like to do, that would be, let's say, cutting edge using the light that was going to be provided by this new accelerator. And so design the kinds of experiments that we would do, design the instruments that could allow these experiments to be done, and the methods that would later be used for analyzing. So not only conceptually, but also organizing teams around. Most importantly, I think my work was always to lead the teams that would do all this work. And leading was sometimes finding the right people to of course, to do the job, which we now have. I think we have one of the most talented teams of engineers, scientists, mathematicians, and technicians and administrators in the world that run this lab. And my role, I think, importantly, once these teams were in place and they were working, was to inspire them on the solutions and the decisions that we have to take for constructing the beamlines. And these decisions are mostly technical decisions, but they are also administrated based on budget, based on availability of technologies, based on compromises that sometimes you have to make so that you can get the instrument you want, not only in the future, but in a few years ahead. So these decisions, normally they have to balance numbers of different kinds, numbers that are sometimes technical, sometimes are economical numbers. Yeah. So throughout this endeavor, I have been always using the Wolfram language as my language of expressing ideas and inspiring the teams that work with me. Yeah? I'm probably the heaviest user of the Wolfram language in the lab, and because also we have a very heterogeneous workplace in terms of methods and language, because there's all kinds of scientific and engineering methods going on in the place. But I think that through all the history of my duties in the project, I was always using this mostly to inspire people that some decisions we were making, they were feasible. Sometimes they were the best ones. Sometimes they were ballparks for exploring further with more detailed engineering tools. But narrowing in the space, the very large space of possible solutions.
I see. And I understand that designing those beamlines were not an easy task. And connected to this, my next question is, where did computation becomes essential to this kind of design, and where does Wolfram Language fills this gap into designing these beamlines?
Okay. Perhaps I can share with you a bit of a presentation with some information, and I think that will give us a flavor of what's going on. Let me give you a hint of what a synchrotron is first, starting step by step. So I'll start with a small animation that was done. It's a combination of animation and real movie shots of Sirius. So this is the light source, looking from outside, is a cellular accelerator. And what we see here is we're coming in this accelerator. Is the first part of the accelerator is a linear accelerator that we call LINAC. Then we have a booster that boosts the energy of the electrons and the storage ring. So the LINAC is where the magic starts. You basically have a thermionic emission cathode that, when heated up, emits electrons. So what you see here are the electrons being emitted by this cathode, and they are accelerated. What you see here is the energy of these electrons as they pass through different structures. And you see that 0.1 GeV, so 100 mega electron volts. This is the real, well, not exactly the real, because we don't have this kind of thing going on in the accelerator most of the time, but the electrons are shot to 150 mega electron volts, to this point where they go through this booster. Okay, the booster is basically to boost. So you see the energy at every round the electrons make, their energy is slightly increased till they reach 3 giga electron volts, 3 billion electron volts. At this point, they are transferred through this transfer line to what we call the storage ring. So this is where the electrons are stored at 3 giga electron volts. And that's where they emit radiation for us. Oh, they emit anytime they are accelerated, in fact, but that's where we collect the radiation of the electron because it's optimal. So what you see here are magnets that provide the bending of these electrons, or the focusing as these sextupoles and quadrupoles. So the electrons, their trajectory is bent through dipoles, and when they are bent, they basically disperse. And then you have to refocus them with these quadrupoles and multiples of magnetic multiples. And they make kind of a dance where they increase size, they decrease size, and the beam size is defined through all these parameters. So these are basically a set of parameters. The electrons are at 3 giga electron volts, so that means that they're ultra-relativistic, which means gamma, which is the Lorentz contraction factor normally used in physics, is of the order of 6,000. So that means in the electron rest frame, for us, the lengths are contracted by 6,000 times. Time is dilated by 6,000 times. Okay. So to give an idea, this is the ratio between the speed of light and the speed of electrons. So it's 0.99999999985. So it's roughly the speed of light. The electrons are very close to the speed of light. And they make this motion, which is modulated by this function. So the electron beam, it increases and decreases. S is the coordinate along the storage ring. This is a phase where the electrons are inside the storage ring. And there's this length of about 20 meters, which is repeated 20 times. So it's about 25 meters that repeats 20 times this dance. The yellow curve is the dance that they make in the vertical direction across these multipoles. So you see this blue is a dipole, and these are quadrupoles and sextupoles. So the electrons make this dance. In the vertical, their size increases and decreases across these different magnets. And the horizontal also, they increase and decrease across the magnets. But this is the phase space of the electron.
Sorry to interrupt you. Just a quick question. Why is this dance is crucial for the beam?
Because as the electron passes, so the electrons are bent, their trajectory is bent by the Lorentz force. So the Lorentz force is caused by magnetic fields transverse to the speed of the electrons. Now, when the electrons pass through a dipole, not all the electrons will face the same force because they don't have all the same speed. So which means that some electrons will make a curvature that is different from the others. that means the beam blows up. So then you have to refocus the beam. So you use the quadrupoles, they work like lenses. And you refocus the beam, so they decrease again. And then they blow up again. And then you focus again. And that's the kind of dance that you have to make it, because you have to always keep refocusing the beam. Beam. Otherwise, it will just blow up. So
it's a continuous correction to the beam.
Yeah, we call it achromat. So you can imagine the parallel with light. Imagine a white beam passing through a prism. Okay. So the prism bends the light, doesn't it? So it bends the light, but it doesn't bend all the colors the same way, because each color has a different wavelength, has a different energy in this case. So the colors are not bent the same way. So the prism disperses light, the white light, into several colors. Now imagine that after the prism, you put a lens. So you will refocus all the colors, and then you put another prism that works the other way around. It takes the dispersed beam and becomes a white beam again. Yeah? Perfect. There's a very nice animation on XKCD that you can find this bend achromat. Basically, it's based on the Dark Side of the Moon poster, where you see the prism, and so the guy sees the prism and is kind of shaky about this, and it puts a lenses to refocus the beam. So essentially, that's the same going on here. You have a bending. You bend the white beam using this combination of prisms and lenses. So for the electron beam, you can think of it as a white beam of electrons, because they have different energies, different wavelengths, not exactly, but different energies. So the dipoles work like a prism. They bend the trajectory, but they disperse. And then the quadrupole works like a lens, and they'll refocus, and then another quadrupole, and so on. And actually, sorry?
No, were you responsible for this specific beam line that you're showing?
No, this is not a beam line. This is actually the design of the accelerator.
Oh, I see.
The teams that designed the accelerator, these are accelerator physicists, and they found the best arrangement of magnets that would produce the smallest electron beam with 3 gigaelectron volts that we could find.
I see.
So they found through very detailed simulations what would reduce what we call the phase space that the electrons occupy. Right, that so-called emittance, but it's essentially the volume of the space the electrons occupy in this dance when they propagate in this the storage ring. This is the role of the accelerator physicists. So basically, then when we have this design machine, we know basically what is the size of the electron beam, so we know what is the source of radiation. What is the size of the source of the radiation? Is the electron beam. The transverse size of the electron beam is the size of the source of the radiation. So the beauty here is now I know it's an electron beam at 3 gigaelectron volts with a certain size that will emit radiation. So what can I do with it? I have to refocus this radiation. I have to bring this radiation to the experiment, refocus this radiation, make an image of this electron beam essentially at the sample point, and then use the result of interaction between the radiation that I refocused into the different processes that happen with matter. Now, the smallest is the size of the source, the more fine is the details of the experiment. So the name of the game here is reducing the source size, because basically you can think of, if I refocus the beam, what is the smallest spot I can get? Well, it's just a demagnification of this electron beam. Right, so the larger the electron beam, the larger is the spot. The smaller is the electron beam, the smaller is the spot in your sample. So the finer is the detail, the smaller. To get fine details like nanometer details in samples, right? If I want to demagnify something, normally 1,000 times the magnification is quite a challenge optically, right? So if I start with a beam of millimeters like it was in UVX and I demagnify 1 millimeter, I get a couple of microns.
Okay.
Now, if I want to do a spot of nanometers, I have to start with the electron beam of micrometers. And that's the beauty of this game. The first electron storage rings in the second generation, let's say, the first generation, it was basically a repurposing of electron accelerators that were used for collisions. electron-positron collisions, typically. Then second generations, they were built for the purpose of extracting synchrotron radiation, okay? And UVX, our old light source, it was called UVX, was a second generation. The typical size of the electron beam, the transverse size in this dance, so the electron is basically, there's an envelope of dance, and this envelope gives you the size. So you see, for instance, here, this envelope, I can calculate the size of the beam, and in this case, it gives us 20 microns by 2 microns. It's pretty small. Just to give a comparison, the old storage ring UVX, these numbers would be like millimeters, okay? So now we have an electron beam source of the order of a few microns only. If I demagnify this by 1,000 times, so roughly in the ballpark of nanometer spot I will get, okay? But obviously this depends a lot on the optics and how I generate radiation and so on. So the dipole radiation, for instance, we get when the electrons, once they pass through dipoles, like here, this is a dipole. So you see the blue is the electron beam. The trajectory of the electron beam is curved. The electron beam continues, and the photon beam in white is what is emitted. So trajectory is curved, the photon beam is emitted. This is the flux. That's where our work in the beamline starts. So what is the characteristics of the radiation? This is a general curve of the radiation of emission. So I see, for instance, 10 kilo electron volts is X-rays, typically we call X-rays. 100 electron volts or 0.1 kilo electron volts, we call soft X-rays. About 30 to 40 kilo electron volts, we call hard X-rays. And below here, we call UV and infrared and so on, visible light, okay? So this is the full spectrum of the light coming out of this dipole. Now, depending on the experiment I want to do, I want to use a certain range of this emission for the experiment. If I want to do an experiment in, let's say, ultraviolet, or infrared? Well, first, there are different kinds of dipoles in the machine. This is the one I showed here in the animation is a large magnetic field dipole. So the Lorentz force is larger, the acceleration is larger, the radiation emitted is harder. It's higher frequency, right?
I see.
So this is why you see this blue curve here is the radiation emitted from this dipole here. Now, there are other weaker dipoles where you have this kind of radiation here. This is a log-log plot. So if I want to extract radiation from this low energy part of the spectrum, I rather use the source of this dipole. If I want to extract radiation in the hard X-ray, I rather extract from. So this is the first part of our design. Now, let's move on. For instance,
just a quick question. This is why we see different sectors in the. So we are decomposing the spectrum in the specific wavelengths that we want for a specific or a target experiment. This is why I saw in your video that you have specific sectors that separate these spectrums, right?
Exactly. These sectors are called beamlines, and we're going to get there. So let me first give you another idea of this is also where Wolfram language was used, Mathematica was used, is when you want to optimize the amount of radiation that you emit, making just one band, because this one band here is obviously necessary, otherwise I don't make the full curvature of the accelerator, right? Okay. But if I want to extract more radiation, I can design several bands in sequence, because each one of these bands produces radiation, right? Mm. So let me show you an example here where we do this kind of design. So this is called an undulator. So a sequence of magnetic dipoles that makes this electrons make the wiggle, and this wiggle produces much more radiation. You can see from this animation, for instance, okay, the electrons passes by north-south poles of this specific range of magnets, and this produces radiation every time they're bent. It produces more and more radiation. This is called an undulator. Now, making the project of these devices requires magnetic simulation, which you can do, for instance, exactly like here, semi-analytically. I used a lot semi-analytical approaches for getting into the ballpark. A lot of this manipulates, for instance, where we can vary different aspects and change magnetic field and change the trajectory of the electrons, and also define optimal regions where the electrons are accelerated in the right way. And from this, calculate, for instance, for this device, the equivalent of the spectral. Now, you see here that we don't have a continuous curve like the other ones from the dipole. Here we have almost like specific bands of emission. This is typical spectral brilliance of an undulator. And why this is happening? Because I have a specific period that the electrons are moving. So you can think of the electron as kind of making the movement of an antenna. But you would say, yeah, but this is a movement. If I look closely to these magnets, this would be of the period of a few centimeters. Yes, but remember that we said that these electrons are ultra-relativistic. So from the electron point of view, this centimeter period of our magnetic array that we have in the simulation actually looks for the electrons as micrometers because there's a strong Lorentz contraction. Now, the electrons emit radiation within this wavelength of micrometers, but they are moving so fast compared to us that the Doppler effect brings this micrometer radiation into X-ray range. So that's why we see this spikes of emission in the X-rays because of and they correspond to multiples of this period of oscillation of the electrons, but boosted twice by the Lorentz factor, once by the Lorentz contraction that brings wavelengths much smaller, and second by the Doppler effect. So roughly this is the physics behind this kind of device. Now, optimizing this device, we used not only myself, but the accelerator physicists that designed these devices. They used a package called Radia, and I used myself as well. And Radia was a package developed by one of the leading scientists that developed the accelerator physicists that developed undulators in the past, Pascal Lhomme, and his collaborators. And this is a package that intrinsically we work on Mathematica, and then we bring together with other packages. Now, after the beam coming out of the undulator, this is only photon beams, right? Now it's X-ray photon beam. Now I have to, what? Bring the photons into the experiment. Now, let me give you an idea what happens once the photons are emitted. Oops, sorry, let me go back. Okay, the photons are emitted, and then they come into some of this equipment that we call monochromator. So all those wavelengths, now they are filtered using Bragg diffraction, and the photons are focused using elliptical mirrors. They are focused into the sample position. Why? Because now you have to demagnify the source, focus on the sample position, and scan the beam throughout the sample to extract different quantities. Now, the design and specification of those mirrors that collect the radiation, they have to be, there's an enormous number of variables, but they're essentially, you can think of them as ellipses. Let me run the simulation again, and you see when I talk about ellipses. So photons come out of the storage ring. They pass through different elements. First, they are monochromatized, and in the design of this device also, we used a lot of simulations. I'm not going into the details of this one, but once they pass through this, and the radiation is purely a single wavelength, this mirrors are the ones that focus radiation. So these are elliptical surfaces. Now, these elliptical surfaces, they are polished down to atomic scale, basically, and they have to be perfect down to this scale. Now, simulating in detail the wave propagation through the surfaces is a heavy computational undertaking. And we have, again, to choose the ballpark of what we want for the science that we want to make. So what kind of beam do you want at the sample? What size of beam? Should it be large? Should it be scanned? Should it be small? What kind of energies, right? So again, we have to run different simulations. And what I'm showing here are different kinds of simulations, semi-numerical analytical simulations, where we define the vertical and the horizontal shape of the mirrors and their position. And in the dots is the final simulation that we have. So basically, we had to first define the ballpark of what we have to choose for the mirrors. The position.
Oh, so you're playing around with the parameters to see
Exactly.
which one
Obviously, I have the ground truth, which was after we chose the parameters, we ran each dot of this is a very extensive simulation, But that kind of semi-analytical model gave me ideas of, okay, what I want is a beam size that is roughly equal in nanometers to the vertical and horizontal. Well, this is not exactly how it's working. So if I change the working distance or I change the mirror length, but when I change the mirror length, I also change in the cost of this mirror. Or if I change the fraction of what I get from a slit or a working distance, that influences a lot also what kind of instruments I have to put inside the instrument. So you see, just give you an idea that I first have to play with the semi-analytical models, define the ballpark of, okay, this is the working distance, this is the mirror length, which is still can be manufactured. This is the horizontal, this is the vertical, this is the angle of the mirror, because it will also, depending on the angle of this mirror, it will cut off some of the energies that go through the beamline. So once we play with that, then we can run simulations and ask the manufacturers if they can make this kind of mirrors. Once they make the mirrors, then we have measurements and we can refeed back into the simulations and see, okay, is this going to work or not? So the kind of work that we do with Wolfram Language was essential for designing to give an idea of the ballparks of simulations for the sizes of the mirrors, on the dynamics of the devices, how stable they have to be, or on the perfectness of the mirrors. We know, for instance, that they all have roughnesses, even though you polish down to atomic precision. The more precise the mirror, the more expensive and the longer it takes. So you have to play with these numbers as well. So do I really need something that perfect? Is it going to cost so much more? So this is the kind of leading directions that someone in my position have to think even before running detailed simulations. Is this good enough, or do we need really to spend much more and much more time designing this? So once we have then the mirrors in place, and we have to design the experimental stations. So for instance, this is the final result. This is one of our experimental stations. We shine the beam through, and then we process this data. And in processing this data that comes out of our detectors, well, defining the detectors also, I have used a lot the Wolfram language to get again into the conceptual design. Mostly I used in the conceptual and preliminary phases of our designs. Now, if I have this, I'm going to give you an example of one specific science project that was designed. Now, what you see here is like an animation, how computers then turn this data into the structure of a molecule, let's say, right? So this is one molecule that was found recently. Brazil is very famous for using ethanol, for instance, as fueling our cars. So Brazil is one of the countries where most of our energy is biorenewable. It's renewable energy from different sources. But there's a lot of biomass that is created when we use, for instance, sugarcane to produce ethanol. And this bagasse of sugarcane can be reprocessed, and we can reutilize the polymers and depolymerize cellulose to get, again, more alcohol. But you have to find enzymes that can do that not so costly, because if it costs too much energy to break this down, then it's not worthwhile. So there's a lot of research going on at CNPM, our center, to find these enzymes. And they use a lot Sirius to guide their discoveries. For instance, this is the structure of one of the newest molecules. Is one enzyme, is a protein that has, if you see this little ball here is a copper atom, and you find another copper atom. So this enzyme uses each one of these copper atoms differently to break down cellulose. And they do a lot of this research using the beamlines of Sirius to do these 3D images of proteins. So let me give you, for instance, this is a comparison on the state of the art compares with the cocktail that we can use here at CNPM. This enzyme is the state of the art of efficiency in terms of breaking down cellulose down to produce ethanol. Now, Some other examples that I used Wolfram Language now in the end of the pipeline of this entire thing is we have results, we have tomography, for instance, and we want to extract some things out of this tomography, right? So I used a lot prototyping, the codes that are being used in the beamlines, what kind of things we want to see. This is, for instance, a microaggregate of soil that we want to see the components and the organization and also the composition of this microaggregate for different purposes. In this case here, it was for understanding how soil organizes in such a way that phosphor is retained in some of its pores. So we can see, for instance, composition of soil using tomography as well. Of course, this is not what the users use in the end of the day. We have specific software for the users of our beamlines. But in my job, that's the kind of things that if I have an idea, I want to express and prototype it conceptually and to give our teams to do something more detailed that will be on the beamlines. That's the kind of workflow that I use in my daily life. And more recently, our newest project is to design a new laboratory that will be the first in the world. It's a BSL-4 laboratory, so it's a biosafety lab that will be the first in Latin America, first. So biosafety labs, they are essential for studying pathogens that are extremely dangerous, that you cannot deal with them in any kind of laboratory, biological laboratory. So pathogens such as Ebola, for instance, they require a specific set of tools and safety management that are not present in most laboratories. So when you see in movies, those scientists wearing these big suits and so on, that's the kind of BSL-4 laboratory. So in Brazil, we don't have one of these laboratories. And the first one is going to be built and is the first in the world that is going to be connected to a light source. So
wow,
we are going
to... Nice.
Yeah, this is going to be the first of a kind. And we are going to connect Sirius to this lab. So what you see here is an image of this lab that is being built. So you see BSL-4 and 3, and there is this part of the laboratory here, which are where we will have cryo-electron microscopy and the first of a kind, the beamlines. So basically, they will be tomographers using X-rays from Sirius that will allow us to see 3D images of cells in the scale of cells, where the field of view is a single cell, or tissues in 3D to study, for instance, how hemorrhagic fever works in the tissue level, cells to see how viruses create factories inside cells, and in the animal level, so it will be another length scale, in the scale of model animals like small rodents and small NHPs, so that we can do in vivo study how these diseases evolve in what we call humanized mouse, for instance. So in designing these beamlines, to begin with, right? When we started this project, can we make beamlines coming into the BSL-4? Yes, we can. But what can we do with that? Because, well, it's interesting to see viruses at the molecular level, but these electron microscopes are more suitable. To see proteins like the ones I showed you, we don't need to be in a BSL-4 because proteins are not dangerous to deal with. But to look at cells, tissues, or animals, then you need a specific environment. So we thought at first, okay, let's do tomography beamlines. Why do we need 3 beamlines? That's first, again, conceptual design, where I have to run simulations and understand using semi-analytical models. Okay, this range of beamlines, I need to provide with a specific kind of undulator, like the one we started discussing. But for using the tomography in mice, I cannot use the same undulator, so it has to be a different device. This device has to be simulated differently, and the optics is completely different. And for tissue, well, it's an intermediate in between them. So designing these beamlines and finding optimal energy ranges, for instance, this is a kind of calculation. What I show here is a simulation of how much exposure I need, how many photons I need to extract images with a certain resolution of 15 nanometers, depending on the tissue thickness and the energy range of this beamline. So from 1 kiloelectron volt to 30 kiloelectron volt. So animals would be classified in this tissue scale of much higher thickness, and cells would be at much smaller thickness. So I can see that I need to use smaller energies to be optimal in the tomography of cells, and a different energy to be optimal in the tomography of animals. This kind of design then leads to different simulations. And for instance,
What are the white squares?
it's something missing here, but it's basically the levels of, for instance, this is level curves for showing 10 to the 6 photons per second, 10 to the, here, 10 to the 7, 10 to the 8, 10 to the 9, 10 to the 10. Yeah, it was just a label in each one of them. But basically, this is a way based on a model. There is a model in the literature that is here. We simulated this model using the Wolfram language and see, okay, this is the optimal energy for cell tomography. This is the optimal energy for tissue and for animal tomography. So they have different energy ranges that I have to use to optimize the beamline. Then comes the engineering part. What kind of undulator I need to fill in this energy range? Oh, this is a different device that I have to simulate from, again, Mathematica. And what kind of mirrors do I need to focus the radiation? So all this process then starts from this. Once I define the energy range, then I have to define the mirrors, I have to define the propagation distances, and this is all done through semi-analytical models that feed in the subspace of variables that I have to find in more detailed simulations and engineering projects. So that is, for instance, now the design of this animal tomography beamline. What you see here is already a more detailed design of how we're going to do this. For instance, the beamlines are not contained in this BSL-4 environment. They are actually, you bring the animals from the BSL-4, but they are connected through these windows, which again, we have to simulate. And the animal sample where we put the animal, they levitate so that you don't have contact of this BSL-4 laboratory with our expensive instruments. So it's all on this design. We'll have to use different kinds of detectors that we are designing as well. And yeah, this is all part of this big game of providing experiments for science. So we basically, our major product, if we want to put this way, that we provide to the community are experiments. In this case, the experiments for doing tomography on organisms, cell or tissues infected with dangerous pathogens. But in the other cases, as I showed, we provide experiments for analyzing soils or analyzing the protein structure or microcircuits or nanocircuits or rocks and the porous states of rocks, or name it. Basically, we provide these kinds of experiments going from what do we want to see in nature with synchronous radiation all the way down defining the designing and building our own instruments. And this is an important characteristic also of our lab, is that we design and manufacture the instruments that we use, that we need to be in the state of the art for this kind of accelerator. And this is all done here in Brazil. We also have many collaborators and companies that we collaborate around the world. But we are proud to say that we created an ecosystem of science and technology in the country around Sirius that is composed by universities that have all the human resources created that we use in the project. We have companies that have gone from what the typical business into the synchrotron business. And we have policymakers and the government. And this is all funded by our federal government in Brazil.
Wow, this is really nice. This is like a very complete and wide answer to a not simple question about how can you use Wolfram language? Because it's really nice that a tool that most undergrads or even grad students use to make plots and make graphs can also be used to make designs of this kind of scientific and engineering experiments. And that actually plays an important role in these new constructions in the Sirius itself. This is really nice. And by talking to you previously, before this interview, you have mentioned to me that you have used Wolfram language. I'm not sure since your undergrad studies or something like this, but when you look back, when you first started to use Wolfram language, for example, and then you start doing some calculations and solve some equations, and now you see yourself in a position of a director of LNLS, for example, where you use Wolfram language to actually develop science and to design new kinds of beam lines as the one you have showed. By looking back, would you say that Wolfram language has influenced you more on how you think about scientific and engineering problems, how you execute them, or specifically in connecting those two aspects on how to think about a problem and how to execute a problem?
I would answer yes for all of your questions, but let me be more specific. Yes, since I started using Wolfram language back on during the end of my undergrad studies in 94, 93. It was in the early stages of the Wolfram language yet.
Do you remember which version?
Wow, I don't. But I remember it was in Sun workstation. And that from that point on, I realized that, well, I think I don't remember which philosopher said that language is the road or the path through which ideas flow, right? And it is the kind of language that allows you to express your ideas, because if you have something, you can quickly connect ideas that would be abstract in your brain, that would be hard to connect. But for me, it was always an easy language that I could quickly program. I mean, you learn the program, you have several languages that we all dominate, but the major difference is all is in your hand, and it's very graphical for analytical things, and you can mix analytical aspects of the language with numerical aspects and with graphical aspects. And this is essential when you're doing a lot of, especially when you're doing nowadays, when you're leading people, because leading is kind of, it's most of the work of leading a large group, and we have today about 360 people working at LNLAT. And we have meetings at all levels where technicians, trainees, and so on. And I think leading is basically inspiring people of going with you in a certain direction, right? And all in the technical world, especially when dealing with such a smart number of people that you have, scientists and engineers, lots of people with PhDs and so on, they are not simply convinced but because you said so. You have to really present compelling evidence that we should go this way and not that way, because it's and sometimes you can only convince if you have a good feeling of these calculations. They can be approximate, but it gives a higher probability that going this way, it has a higher probability of success. We all come with our prejudice, our priors of where we should go, yeah. But mathematics always helped me to increase the likelihood of convincement. So I'm very Bayesian in this sense, but I'm always trying to show people that there is a higher. We're never certain which way we have to go, but we can increase the likelihood of our thinking and going from our prior, which are normally prejudices, or based on our previous experience, based on, because we like something. We are human beings. We sometimes make technical decisions also subjectively, right? But having a good language that can help you express ideas, and for yourself also, for myself, several times, as you said, I used the Wolfram language to convince myself I was wrong, or convince myself that, okay, this is the right way to go, by putting things together and plotting just the right graph, because with a simple command, plotting the right curve, that will say, oh my God, this is what I should have plotted from the very beginning. It's not a complicated thing. and I could access this data and convince people just with this one simple graph. Yeah, and I think this is really where things shine for my point of view.
I think that's really nice because, for example, you have shown a lot of manipulate graphs, and sometimes you have a complex function that you have many parameters, and sometimes the best way to understand what this function describes is to play around with them and see which parameters, what each parameters do when you change them in the function. So this is something that's really amazing. Of course, if you have a static plot, you can extract information, but if you can also play around with it, this changes the way not only you demonstrate to other people your ideas, but in some sense, how you learn about that.
Exactly. Yeah. You're absolutely right. This manipulate has been one of the favorite tools for especially when we have to play with so many variables, because sometimes, yes, it's the feeling that you have. Okay, I have a feeling that going into this ballpark combined with that numbers and so on. Of course, you can do that by hand, but having the tool that allows you to do instantaneously things like that, and you know that behind that is running a very complicated, sometimes even numerical calculation around it. It's really decisive it's decisive in showing the right perspective of a complicated problem, and sometimes the perspective can correspond to several IQ numbers for anyone.
Yeah, exactly. And there's so much you can do with this language. And you have also the possibility of, I'm not sure if you're aware, but there is a Wolfram repository Packlet where users create some Packlets for Wolfram language that you can actually install it and get all of this stuff from that other people created, other experts, for example, in chemistry and biology and in many fields, and then you can extend what Wolfram Mathematica, for example, can do. So this is pretty amazing.
I'm not very familiar with that, I have to confess, but I learned that recently, and I'm very excited to use it. And not only to use things that other users have done, but also putting some of our things into Packlets that can be more easily used, because we share a lot sometimes this Wolfram notebooks, but sharing Packlets is way much easier from what I learned. It's more general.
Yeah, and for example, there is a website that's called Wolfram Demonstrations. I think you know that, right? The prerequisite to post, any user can post them, but they ask for demonstrations that use, for example, manipulate. It has to be used like that because you should demonstrate. And then you showed, for example, a lot of manipulates. For example, when you show the beam line with a specific array of magnets. I would suggest consider posting that on Wolfram Demonstrations as well, because it would be really nice. And it's amazing to see that you mentioned to use Wolfram language since the end of your undergrad studies, and many years after that, you're now using the same language to dictate and to make the design of very specific parts and very important parts of the Sirius or the LNLS. So it's really amazing to have your story shared here. And with that, I would like to thank you very much for agreeing with this interview. And thank you very much for sharing a little bit about how Wolfram language was used, and it has been used in the Sirius in the Brazilian Synchrotron Lab in Brazil. So thank you very much, Eric.
Thank you, Lucas. It was a great pleasure.